So I have three different scenarios here of a cell being immersed in a solution. And the cell is this magenta circle, that's the cellular membrane. And then I have the water molecules depicted by these blue circles. And then I have the solute inside of the solution, inside of the water solution, that we depict with these yellow circles. And I've clearly exaggerated the size of the water molecules and the solute particles relative to the size of the cell, but I did that so that we can visualize what's actually going on. Now we're going to assume that the cellular membrane, this phospholipid bilayer, is semi-permeable, that it will allow water molecules to pass in and out. So a water molecule could go from the inside to the outside or from the outside to the inside, but we're going to assume that it does not allow the passage of the solute particles. So that's why it's semi-permeable. It's permeable to certain things, or we could say selectively permeable. Now, what do we think is going to happen? Well, the first thing that you might observe is we have a lower concentration of solute on the outside than we have on the inside. So at any given moment of time, you will have some water molecules moving in just the right direction to go from the outside to the inside. And you will also have some water molecules that might be in just the right place to go from the inside to the outside. But what's more likely to happen, and what's going to happen more over a certain period of time? Well, the water molecules that are on the outside, and we talk about this in the osmosis video, they're going to be less obstructed by solute particles. If this one happens to be moving in that direction, well, it's going to make its way to the membrane and then maybe get through the membrane. While something, if this water molecule was moving in this direction, well, gee, it's going to be obstructed now. Or maybe this is bouncing back and it's going to ricochet off of it. So the water molecules on the inside are more obstructed. They're less likely to be able to fully interact with the membrane or move in the right direction. They're being obstructed by these solute particles. So even though you're going to have water molecules going back and forth, in a given period of time, you have a higher probability of more going in than going out. And so you're going to have a net inflow of H2O, of water molecules. Now, a situation like this, where we're talking about a cell and it's in a solution that has a lower concentration of solute. It's important that we're talking about a solute that is not permeable, that is not allowed to go through the membrane. The membrane is not permeable to that solute. We call this type of situation, this type of solution that the cell is immersed in, we call this a hypotonic solution. Hypotonic solution. And anytime we're talking about hypotonic, or as we'll see, isotonic and hypertonic, we're talking about relative concentrations of solute that cannot get through some type of a membrane. And the word hypo, you might have seen it in other things, it's a prefix that means less of something. So in this case, we have a lower concentration of solute in the solution than we have inside of the cell. And because of that, you're going to have osmosis. You're going to have water molecules going from the inside, or you're going to have water molecules going from the outside, I should say, to the inside. And that's actually going to put pressure on the cell. The cell itself might expand, or it could even, if there's enough pressure, it might even explode. So now let's go to the next scenario. In this scenario, we have roughly equal concentrations of solute on the outside and on the inside. At least I tried to draw them that way. So in this situation, the probability of a water molecule in a given period of time going from the outside to the inside, or from the inside to the outside, is going to be the same. And so you're not going to have any net inflow or net outflow. You're always going to have water molecules going back and forth, but there's not going to be any net inflow or outflow. And so in this situation, so let's see, let me write no net flow. And this type of solution, where you have the same concentration of solute in the solution as you do inside the cell, we would call this an isotonic. This is an isotonic solution. Isotonic solution. And the prefix iso refers to things that are the same. It has the same concentration of solute. And so you have no net inflow. So hypotonic solution, you have water molecules going into the cell expanding, kind of like a filling balloon. Isotonic solution, no net flow. And then, of course, you could imagine in this last scenario, I have a higher concentration of solute on the outside than I have on the inside. And we can guess what's going to happen. So first, what would I call this? Well, I have more of something in the solution, so I would use the prefix hyper. I have more of it, more hypertonic. This is a hypertonic solution. And once again, the solute can't go across the membrane, but the water molecules can. And you're going to have water molecules going from the outside to the inside, and from the inside to the outside. But the probability that the ones going from the ones on the inside are going to be less obstructed to go out than the ones on the outside to go in. And so you're going to have a net outflow. You have a higher probability of things going from the inside to the outside than you do from things going from the outside to the inside, because they're going to be more obstructed. And so they're going to be held back, I guess, in different ways. So in this situation, you're going to have the water escape the cell, and the cell actually might shrivel up. The cell, since it's going to lose that pressure from the water, the cell itself might shrivel up in some way. And you could actually see this in actual living systems. If you were to put a red blood cell into a hypotonic solution, the water is going to rush into it, and it's going to blow up. It's going to expand. And so it's going to look like a overinflated red blood cell. In an isotonic solution, it's going to look the way that we're used to seeing a red blood cell, actually having kind of that little divot in the middle area, while over here it's all going to expand. And then in the hypertonic solution, the water is going to escape the red blood cell, and then you would actually see it kind of shrivel up a little bit like this, because all of that water is, we have a net outflow of water molecules.